Hi, everyone. Happy Friday. My name is Jihei Moon, and I'm the Assistant Director of Education Programs for LEAP, or Learning the Earth with AI and Physics, at Columbia University School of Engineering and Applied Sciences. We're just housed under Columbia. We're not a Columbia program, but we have to have a home. LEAP is a National Science Foundation funded science and technology center, which our program director, Pierre, will introduce shortly. After that, we will get into the details of LEAP's research experience for undergraduate students, or REU, with one of our mentors, research mentors, Mike Pritchard. Then I'll review the application, eligibility, and next steps before we go into Q&A. So that said, please hold your questions until the end of the session, or you can chat me directly if questions come along, and we can go over those at the end of the presentation. And I will have Pierre get started.
Great, yeah, thanks so much, Gia, and welcome everyone. That's exciting to see you interested in this topic. So maybe just to give you a little bit of background. So we are actually what we call an STC, so Science and Technology Center. So it's one of the largest sources of funding from the National Science Foundation, which is this federal funding agency for science as a whole in the US. We are partnering between Columbia, NYU, UC Irvine's actually, Mike Pritchard and Stephen Mant are actually professors there. Teachers College right around the block here at Columbia, and University of Minnesota as well. And what we are trying to do is really trying to get to the next generation of climate modeling, and really trying to think about what we call climate data science. So trying to really merge two disciplines, at the interface between data science and climate science, and with the hope really to kind of lead to the next generation of climate projection. So typically what we do is we use a model. So this is a typical climate model here, very, very pixelated. It looks like an old video game, if you will. And what we are trying to do is to do something much more precise, a little bit like what you have on the right-hand side. We want to see clouds really well. We want to represent the future really well. And that's kind of the ultimate goal. So it's not just about resolution, but really about better physics and better representation of a lot of different processes, because those models are trying to do a lot of different things, from representing the carbon cycle to representing clouds to representing precipitation and whatnot. So we are just trying to do a better job overall. So, and the reason for that is we want to give everyone, and basically a wide range of stakeholders, from the public to the private side, we want to give them much more accurate what we call a projection, which is a prediction ahead of time, especially by the end of the century. And we want to do that and be as precise as possible so that people can plan. So if you think, for instance, about infrastructure planning, you need to know what's going to happen. Like what is going to be the typical level of a flooding event 20 to 30 years from now? What's going to be sea level rise if we want to build a wall? What's going to be sea level rise by 2060, say in New York City? So we need to have really accurate and precise information. And kind of the unfortunate truth is that a lot of the current generation of models are really not up to the task. So we want to change the game, and we want to have models that are more useful, if that makes sense. And feel free to interrupt, if you have any questions, I'd be happy to, if anything is unclear. So the way we formulate that is so that's our mission statement. That's when you have a strategic plan, you have a vision and a mission statement, like for any type of, like typical companies also have that. And our mission is really to provide some sort of leap forward in reliability, utility, and reach of climate projection through that synergistic innovation between data science and climate science. And the way we see that, and what we mean by reliability, is that we want to really start thinking about data-driven climate projection. So really putting data as a core component of climate projection. And that's not something that's happening right now. Typically now it's kind of an afterthought. You build your model, based on some, thoughts you have about physics or physical processes. And then you have some basic checks, does the temperature of the globe looks reasonable or not? Some basic things, right? And now what we want to do is we want to plug a lot more data. We want to say, we have plenty of satellite observations, we have plenty of measurements. Can we plug that into the development of those models? And can we use AI in particular to improve those models, if that makes sense? We want to also improve the utility. And what we mean by that is that there's a little bit of a disconnect. So, and we've witnessed a lot of that for COVID as well, is that, you know, even the best scientists in the world, if you're trying to do the best science in the world, you need to connect, right? You need to connect to real world impact. And to do that, really what you need is you need to have a way to provide the data, and in that case, climate information and basically those projections in the future. You need to provide that and put that in the hand of the people. And you need to do it in a way that's easy to use, that's easily accessible, and that's public, you know, and shared with everyone. So that's also something we want to do, is having a platform where people can basically get the data. It could be even on a laptop. That's what we are actually working on right now, where they can see, okay, what's going to be the conditions in New York by, say, 2060 or 2070? Can I get that directly on my laptop? Can I use that for, say, my company or for my, you know, public sector or public agency? So that's what we also want to do. So really making climate data much more useful, you know, and providing that to a wide range of users. And we also want to extend the reach. So that's actually very connected to that, having basically this cloud infrastructure and everything, all of the data on the cloud, so that people can use that for their research, for the education. So that's part of this research experience for undergrads, where a lot of the data will be on the cloud, but also using the same data for all of the public and private stakeholders. You know, they will use the same data. We can replicate everything, and we can like really strengthen also this pipeline in terms of having a much broader use of climate data, and also a much broader community of data scientists and what we call climate data scientists. So again, people that are really well versed in terms of climate and data. And we want to really reach out a crowd that's diverse, because climate is affecting everyone. So we want to also be representative of society, so we can really act on climate, you know, and especially with the climate crisis, so that we actually represent society as a whole. And finally, kind of how we see that, we believe that there's quite a bit of novelty in terms of the fact that we hope to be some of the first ones to really leverage and really advance the use of data science across the entire climate model pipeline, in the sense that we want to use a lot of the existing data platforms, again, such as satellite data, et cetera, to improve climate models, but also using data science for the post-processing or for the use of those data. Like, how can we provide a ton of data to the users on a laptop, right? You want to go in with your laptop, you want to zoom into a region of the world. There are huge technical challenges because we are dealing with petabytes of data. So how can you do that efficiently? So, so really, we believe that improved and much more advanced use of data science and AI across the different pipeline of the climate model is going to be really leveraging, first of all, improving climate models, but also making climate model data much more accessible to a much broader community. And we believe that this is how we can actually help with the climate crisis, and especially for climate adaptation, if that makes sense. So kind of the roadmap, so that's a little bit how we see the center. So we have this connection between climate and data science. So we call that climate data science. We see that in terms of education and research. So we are training a new generation of scientists within the center and the satellite institutions, but also through some research exposure, such as this IU program, you know, where we really want to connect different groups of individuals, people that have different skill sets, and by working together, working in tandem, working in groups and in pods, we can actually create that synergy between disciplines, and people can basically learn from each other. And we believe that this is how we can actually generate or create this kind of new generation of models where people can actually really use data at scale. You know, they can actually use and develop better climate models that are also more useful for society because they are more precise again, and then more informative, you know, of what's going to happen next. And then we have on the right-hand side, we have what we call, again, this bidirectional knowledge transfer, in the sense that we want to provide the data that we are creating, in particular, moving forward. We want to use and provide this data to a wide range of public and private stakeholders, so that they can really use data and they can act against climate, especially for climate resilience and climate adaptation, because they will have the right type of data and they could therefore plan in advance and be more resilient and adaptive to that. And we see that as really throughout the entire center is broadening participation as well. So again, because we believe that climate is affecting everyone, there's actually a very tight connection with social justice as well. So social justice and climate justice are tightly connected. Actually, I just read yesterday there was a very nice poster on the subway yesterday about that. So those are very tightly connected topics, and that's why we believe it's really important to broaden participation at all levels of the center. And finally, to really do that, we need a modern data infrastructure. So this is the so-called Pangeo, and we call that LEAP Pangeo, so the fusion between LEAP and Pangeo. It's a modern cloud data infrastructure, especially for climate data, where you can basically do a lot of the compute on the cloud, and therefore you don't need to download everything on your laptop, right? So you can actually do a lot of the compute on the cloud. And that's what we also want to leverage in that RU. So that you don't need to download all of the petabytes of data, which is impossible on your laptop, but actually doing that directly on the cloud. And also that in that sense, it's also much easier to replicate and to share code, right? People can redo the exact same thing. It's not dependent on your particular platform, your particular environment, but that's something we can easily replicate. So that's actually very important for us. Next. Thanks. Yeah. So we kind of see that as on the science front in terms of two what we call challenges. The first challenge is to, again, develop the next generation of climate models, so models that are way more precise, and we do that by basically trying to have this combination of new algorithms, so not just off-the-shelf type of algorithms, but potentially also trying to develop algorithms that are more physically based as well, so AI that can include physics or causal mechanisms as well, and that can efficiently leverage observations such as from satellites or a lot of point data that we have across the globe. And also some simulations that we call high fidelity simulations that are really precise, like on the bottom left, you can see a simulation of clouds, which is basically at tens of meter scale. We can see like very tiny details of clouds, and we can use that, but we cannot run that forever because it's very computationally expensive. But we can still leverage a lot of the information that is coming from that. So we really want to harvest a lot of those different data streams that are pretty diverse, but we want to combine that together as a way to basically improve how we represent physical processes in climate models. And again, with the hope that at the end, so really on the right-hand side here, that it will lead to more accurate climate projections so that people can act better against climate change. Next. And on the algorithmic part, so especially for the computer savvy people in the room or the statisticians in the room, so we are trying to also develop new types of algorithms, and especially in terms of algorithms that could actually include physical and causal knowledge, as I mentioned before. And the reason for that is that we don't want to just fit data. So and now we're being exposed to ChatGPT. So every year it's actually even more exciting what's going on with AI. But what we want to do is we have this big challenge that we've never seen climate change, right? Or we are just witnessing a kind of a small version of that or a small amplitude of that. And we don't know how the future is going to look like, right? So it's a little bit different from like computer vision or natural language processing, where we have this huge amount of data and we just want to replicate a lot of the data, right? In our case, we don't want to just replicate, we want to extrapolate, right? We want to predict the future, right? So it's a huge challenge, even from a machine learning or algorithmic perspective, but it's also super interesting. Like, how can you learn from the past to actually infer the future, right? When there's a shift in distribution, when things are non-stationary, right? So it's super interesting, a lot of interesting challenges as well. And that's one thing we are trying to do. So trying to see maybe by bringing in some physics or by bringing some causal inference or causal knowledge, maybe potentially that could help. And we could actually develop better algorithms that can better extrapolate into the future. And just quickly on the education side, so very similar to what we discussed before. So we are trying to create this kind of new discipline, again, at the interface between climate and data science. And we have to deal with a lot of challenges, right? So people have different jargons, people have different vocabulary. So for instance, a typical example would be, a machine learning person will tell you, I have this model. And then a climate science person will tell you, I have this model. And they mean very different things, right? Is it a climate model or is it a machine learning model, right? So those are huge challenges that we need to face and we need to basically solve. And we are really trying to bridge the gap by especially research immersion, right, where people can actually work in tandem, but also creating new classes that are really at the interface between those two things. So, for instance, I have a class on machine learning, but applied to environmental science and engineering. There's one class which is this so-called climate prediction challenge, where it's like an immersion class, where hands-on, where we try to work on a project really to using climate data and doing some machine learning and statistics on climate. So we are trying to bridge that gap between the two different disciplines. And as part of that, so we do that at different levels. So there's this RU program that we have here. We are supporting graduate students as well. And we will have also a summer program for K-12 teachers as well. So they can also communicate that to the high schoolers. And again, across that, we also want to increase representation of underrepresented minorities. And again, because climate is affecting everyone, and we need to have basically a lot of voices that actually represent society across. So I think that's all I had, and happy to take any questions, or we can leave that to the end, however you see fit. Thanks, Gia.
Is it all right if I ask a question about, I noticed with the models, which model would you say is the most common? Would you say it's neural network with machine learning, or are there other ones that are kind of taking over?
On the machine learning side, you mean?
On the machine learning side.
That's a great question. Yeah, there are many different things. So we are using, of course, some neural networks. I mean, there are some more sophisticated things. So, for instance, Stefan Mant is a computer scientist. He has been doing a lot of things also on dimensional reduction, using a lot of more, more recent models as well. So it's not just standard neural networks, but there's kind of a variety of tools as well. Maybe, Stefan, you want to talk more about those things, yeah? What you've been excited about recently.
Yeah, absolutely. Welcome everyone, and thanks, Pierre, for the great introduction. So yeah, there are lots of exciting neural network models being used. First of all, you can of course treat climate prediction as a supervised problem, where you can almost think of the sequence of atmospheric clouds as a video that you would like to forecast into the future. And it turns out in machine learning there are many recent video prediction models that have been proposed, for example. And the interesting part is now, with all the excitement about generative AI and diffusion models, there's actually a lot of use cases for these kind of generative tools also in climate science. For example, you might want to hallucinate lower level details of clouds that you cannot really represent numerically because it's too expensive. So then you want to kind of take a coarse simulation and fine grain it and generate all the low level details to that simulation. But there are also use cases of unsupervised learning. For example, you might want to look at all the data at present temperatures, all the possible climates that have been simulated, and now you simulate everything at global warming, and you want to quantify how strong is that distribution shift, and then what can we learn from that. And for example, the three of us here on the call have already joined work on this. If you're interested, you can look it up on the web. Yeah, those are just a couple of examples.
Any other questions?
I had a logistics question. Could you tell us more about what the 3 weeks before the program actually kicks off, like the virtual boot camp, like what that looks like, or what it is?
Yeah, so we'll actually be talking a bit more about it over the next few slides. And so once we go over those and you have more questions, definitely let me know later, okay?
Yeah, my bad. Okay, thank you.
Sure. Mike, do you want to get started?
Sure, yeah, let's dive in. Okay, so yeah, I guess this overviews some of the components. You've alluded, Samarth, to the 3-week momentum bootcamp. We'll learn more about that. And maybe I'll let Jihei speak to these elements afterwards, but I'd like to drill down into the specific project that we have in mind for the REU. Can we go to the next slide? And the next one. Okay, right. So for the research, Pierre, Stefan, and I will all be acting as mentors. The big picture here is about clouds, in my opinion. So these are stratocumulus clouds. I live next to them in Southern California. I'm a professor here at UC Irvine on the West Coast. And how these clouds will respond to climate change is a huge question, multiple trillions of dollars. If they shrink like ice sheets, making climate change worse, that's going to add more hazard, geopolitical and wildfire and all the rest, because a warmer planet with darker ocean surfaces that are more absorptive. If they thicken up, which they might, unlike ice sheets, it's a less hazardous planet. So there's really big, extensive questions attached to these questions about what clouds will do as the planet warms. And Pierre mentioned the limitations of climate models, and fixing those with AI is one of our goals in LEAP. And we know that climate models cannot afford computationally to represent the details of cloud forming processes. So that's part of the context for the summer project. We go to the next slide. Now, specifically, what we want to do is to target a particular simulation approach that allows us to make progress with testing the potential of ML for this problem. It's called multi-scale climate modeling. Usually in climate modeling, what we do is we carve the world up into little grid cells, and the grid cells are too big to resolve cloud physics. And because we have to cover the whole world with resolution and simulate the whole world for 100 years. So there's a limit computationally on how high res you can be. Multi-scale cloud models sort of sidestep this problem by putting high resolution physics in, but just in little patches of atmosphere that are separated from each other and periodic. So it's a way to sort of get high resolution physics in ahead of schedule. If you make a few idealizations by confining them to 2 dimensions, et cetera. But the key point is that in these multi-scale climate simulation, there are arteries between high resolution physics and planetary climate dynamics. And these arteries become excellent machine learning targets. And they contain a lot of the complexity of learning even more complicated forms of high resolution physics like stochasticity and chaos. The micro models are chaotic models that produce little clouds. And complexity, they involve the mixture of turbulence and microphysics and radiation that adds up to the important effects of clouds on climate. And then also importantly, these multi-scale climate models allow convenient ways to learn machine model surrogates for the high resolution physics that once trained, you can couple back in and look at multi-scale machine learning hybrid physics simulations, a new way of doing climate simulation. So there's an easy way to implant surgically the trained machine learning models. So that's some of the context. So our RU program is going to be focused around the opportunities in these multi-scale climate models. Next step. And we're excited because LEAP has championed the development of the best ever version of one of these data libraries. It's hot off the press with some of our collaborators who build climate models in national laboratories. And so that's important because they've made sure to go through the code with a fine-tooth comb and make sure all the causatively complete ingredients are there for everything that comes into the micro models and everything that comes out. And we've also advanced from this sort of work has been happening for 5 years or so, but mostly in fictitious ocean covered worlds. And this data set now includes the challenges of real geography that you want to lean into for operational climate prediction. And so, yeah, the point here is that we're trying to expose RU students to real world research on the frontiers of this kind of work. And that means you'll be able to pipeline relevant data variables, relevant formats that are relevant to modern climate simulation. And we're designing the data set to have 2 tiers of ambition, one of which is coarse resolution, so the data volumes are not super difficult, and then one of which is operational resolution. And there's bigger challenges of trying to scale performant machine learning when you want to work in that limit. So a few opportunities. Next slide, please. Yeah, and I want to present this as sort of like the MNIST of climate simulation, AI climate simulation. So MNIST, for those who don't know, was an important step along the road to the disruptive image recognition deep learning revolution we enjoy today, which began with a simple toy problem of categorizing digits. But coordinated competition and curated data sets around that problem really paved the way for advances that we now enjoy. And yeah, so the spirit of this exercise is that LEAP is trying to make a climate MNIST, and you could be one of the first to work on it, that contains the essence of high resolution physics in these multi-scale climate models, and sidesteps some of the complexities of non-locality, but includes a lot of the complexities of stochasticity and high resolution cloud physics. Okay, next step. So some of the learning outcomes here are that you'll be trained in machine learning operations. You'll have to work on quality controlling input data. You'll have to work on data engineering, the sorts of things that people in tech companies have to do all the time. You'll have to build training pipelines to do machine learning. Maybe those training pipelines will have to be really performant if you want to work on the ambitious data at high resolution, the large data libraries. You'll have to do the things like assessing the goodness of fit. You may tinker with different loss functions, different ways of measuring skill. Pierre mentioned and Stefan mentioned the opportunity of exploring new algorithms. So there's advanced possibilities here of using modern methods that can learn multimodal physics that are generative, that are stochastic, including variational encoder decoders or generative diffusion-based models. Yeah, so a tier of opportunities. But the goal is to get you to do frontline stuff. Next step. Yeah, and it's possible things could work out great, right? If anybody happens to get a really great fit for these data, it's a brand new data, no one's tried to fit it before, then at the end of the summer, there could be opportunities to continue it on. We are motivated to test provocative good fits that are exhibiting nice offline error skill scores and taking those machine learning models and implanting them in the climate model, which is a much richer testing environment where the imperfections of machine learning can feed back with fluid dynamics. And that's another big research frontier, but one that takes a longer than a summer to really explore. But you can see the extensions of how this work on fitting this data library might evolve into implanting promising machine learning models in hybrid simulation codes and examining the pathologies, and hopefully the successes that emerge there and push us along the path that Pierre mentioned of enriching today's climate simulations with AI submodules. So these are the granular steps that move us along that path and the focus of the summer. And I think that's it. Jihei, you want to move to logistics?
Before we go a little bit deeper into the logistics of things, does anyone have any questions for Mike while we are still on the research end? Well, you have some time and you can think of more questions if you'd like. So to go over some logistics, so the first 3 weeks will be entirely virtual. This is a change from last year. Last year was the first time that RU for LEAP was that was our inaugural summer. And after that, we've made a couple of changes to make things a little bit better for our undergraduate students and kind of offer a more robust and enriching experience. So the first 3 weeks will be a boot camp online. And this will be 1 to 2 hours of live class per day, likely in the morning, and we will get you that schedule later on. And this will also be 4 hours of self-guided learning, about 4 days a week in the first 3 weeks. After those first 3 weeks, campus move-in will be on June 25th, which is a Sunday. And then the Monday after that, your research will begin on campus, depending on what you will be working on. Over the summer, we'll have weekly enrichment and social events. There will be mentorship opportunities with graduate student mentors. And finally, the program ends on July 29th. But to go over in a little bit more detail what the virtual summer, the Momentum Bootcamp will look like. To go back. The first 3 weeks will be, week 1 will be with Dr. Julius Fusecki. He is our data and manager of data and computing at LEAP. He will be covering data, computing, and collaboration. Candace Agonafir will be going over foundations in ML and climate modeling. And then finally, Dr. Jung will be going over paper reading and presentation. So these are all skills that we are hoping that you have going into your research so that everyone is kind of going into their summer research on the same page with, similar skills and making sure that everyone is set up for success throughout the rest of the summer. Okay. For eligibility and application. So I'm hoping that everyone here has already taken a look at the application. Eligible students include rising sophomores, juniors, or seniors in the fall of 2023. So if you are graduating this May, unfortunately, you will not be eligible. We are also working with current SOARS proteges, and applicants must be a US citizen or a permanent resident. If you have any specific questions about that, feel free to reach out to me directly over email, and I'll get you the email address soon. The application is due next Friday at 11:59 p.m. We would need your resume, a transcript, it could be unofficial, a statement of interest, and a reference who will provide a recommendation letter. And that can be sent to leap@columbia.edu. All of the application information is on this link at the bottom, which you will also receive after this session. And some important dates, again, applications are open, deadline is next week, and you should know by the end of the month whether you will be joining us on campus. A few frequently asked questions are here. Can students reach out to LEAP researchers directly? We prefer that you don't. If you have any questions, please reach out to leap@columbia.edu and we'll get those questions answered for you. The program will be hybrid this year. So again, the first 3 weeks will be virtual. You can tune in from wherever you wish. I think that flexibility is nice for the first 3 weeks. And then the last 5 will be in person in New York City. Summer housing will be provided for those that are not already local students, and you will be on campus in the Columbia University East Campus dorms. I mentioned this earlier, but international students are not eligible to apply. If you have specific questions, again, please reach out. And finally, the stipend for the 8 weeks. In addition to the housing, the stipend for the summer will be $5,400. So this gives you a bit of flexibility to, spend time in New York in person and, have a good time in New York while you're also engaging in some really cool research. Again, the link to all of the information is at the bottom. We'll get you this recording as well so that, you don't miss anything. And we'll take any questions if you have any.
I have a question about the application. So I was wondering, is there any specific courses that you should take before you apply? Like, do you need to know like the basics of like machine learning or physics or any other courses before you apply for this program?
I will let Pierre, Mike, and Stefan go answer that question.
I mean, we will have some tutorials, but we will also have some online tutorial that we can provide, especially for the use of the Pangeo platform, especially basically cloud data infrastructure, and also for the use of machine learning, especially the basics, neural network and some deep neural network. So this we can totally provide.
Okay, thank you.
I had a question about the SOARS affiliation. So do we also have to apply then? Because would that be a whole nother process of applying and doing that same thing again with you for the LEAP, I guess, email with the information you provided, or how would that work?
If you could submit an application regardless, we will be coordinating with Kadedia to see what that format is going to look like after we review application. So definitely submit an application. I think I have some information already, but definitely submit so we have it all in one place. Any more questions?
So during the main sort of research portion of the summer, will students be working in teams or individually? And how often will we be meeting with our mentors?
Mike, Pierre, and Stefan, I don't know if you want to go over the research piece of this, but in terms of the social in-person piece, we will definitely have at least once a week in person on Thursdays for you all to come in person to the Innovation Hub located in the Manhattanville campus of Columbia. So you will be expected to join us in person at least once a week for group work. That can also be happening virtually, and I'll let Mike and Pierre and Stefan go over that.
I mean, the hope is again to team up to some extent. So the expectation would be to have like specific subtopics that could draw like a few students together, so that you can collaborate on some pieces of code, ideally across disciplines as well. And then there's going to be some mentoring directly from PhD students on a more regular basis, and then once a week, basically meeting with the PI, so the three of us, so that you have basically 2 interaction points, because also like typically my experience or our experience is that especially undergraduate students sometimes don't feel super comfortable talking to faculty members, it's just like maybe age that we are aging. So it's nice to have like a PhD student, they feel a bit more comfortable asking like more routine type of questions, especially about coding and things like that. Makes it a bit less, can I say, intimidating, let's put it this way. So it's good to have those 2 pieces of interaction.
And I think your question about whether you're working in groups is a really good one, because part of the goal of the center is to champion the new field of climate data science, and certainly we're aware of the software engineering and team programming benefits that you can also see in industry as something that we want to mentor on. And so that's where I think the existence of this central computing hub, this Leap Pangeo computing resource, which I imagine you'll be trained on in the first 3 weeks of this program, will hopefully provide a place to congregate and conditions for team sort of self-assembly. But it's always difficult to predict whether a team will gel and whether one will ignite, but we very much want to foster that sort of experience, because the technical skills are shared more efficiently that way. And I fully agree with Pierre that this tiered mentorship strategy of having PhD students doing this work on the front lines who are really better equipped to transmit those tools to you as well is a big part of the plan.
Thank you.
Any more questions? Great. Okay, I'm going to take that as a no, there are no more questions, but again, you know how to reach us, leap@columbia.edu should any questions come up, and I will be responding to those. Yeah, let us know if you have any questions about the application. The link to the website, I will actually drop into the chat right now in case that's easier to access. Okay, great. That is everything that we have for you today, but again, reach out with any questions that might be more specific to you. And thank you, Mike, Pierre, Stefan, for joining us.
Thanks a lot. Yeah, and the data is really exciting. So maybe we could share later some cool videos or some cool animations. It's pretty impressive to see like those small details about the clouds, etc. It's really cool stuff. Thanks everyone. Have a great weekend.